Guys, so our goal for today is to simplify rational expressions. It's like reducing fractions basically. It'll be a little bit more complicated, but like here we have a fraction. If we reduce that by dividing the top and bottom by 2, I get 2/3. It's the same fraction as it was in the beginning. It's just reduced. Okay, so we're going to do the same thing, but we're doing it with rational expressions, which are fractions also, but they're fractions that have variables in them. So let's go ahead and jump in here. This example 1 here. Where'd it go? So we'll call this example 1 here. Go ahead and write that down. Okay, so we're going to reduce that like we normally would. 20 over 16. What goes into 20 and 16? 4. So I'm going to divide the top and the bottom by 4. So that would be 5 over 4. The V's, on the other hand, let me show you something on the side. You don't have to write this, but I'll show you. V to the 5th power, that means we have 5 V's being multiplied together. V to the 4th power means we have 4. Right? Well, V divided by V is 1. Anytime you divide something by itself, it equals 1. So basically what we end up with is 1 times 1 times 1 times 1 times V, which is just V, right? Now, here's a faster way to do it, though. We have 5 V's on the top, 4 V's on the bottom. Just subtract them. How many are left? 5 take away 4 is 1. That tells me I have 1 V left, and it's on the top. Why is it on the top? Because the bigger one was on the top to begin with. So, there's that. So let me give you another example real quick. Once again, you don't have to write this, but I just want to demonstrate the power thingy a little bit. If I have V to the 20 over V to the 19, we'll say 15 actually. How many V's will be left? 5, and where will they be left? Top or bottom? So it'll be V to the 5th on the top, right? Now if I reversed it, I had this, we still have 5 V's left, but it'd be on the bottom, right? So that one would be, does that make sense? Yeah, just subtract the exponents basically. So subtract them and put the answer wherever the bigger one was at the beginning. But back to the original problem, we basically have 2 things that we want to do. We have the numbers in front, just reduce them like you normally would. Find what divides into both and reduce it. And then you have the letters. For those, you subtract and put it wherever it goes in the top or bottom, depending on where the bigger one is. Okay? All right, so you guys give that one a try. All right, so remember today we're simplifying rational expressions. This is one type. These are what we call monomials. Let me show you the whole sheet I'm going to go through today with you guys. Hopefully we'll get through all of this. But these are monomials where you just have one term on the top and one term on the bottom. The rest that we're going to look at today are going to be more than one term on the top and bottom. Okay? For those ones, we actually have to start by factoring in order to reduce. Okay? So these guys are a little bit different in the way that you handle them because you don't have to factor. And these ones down here we do. So let's go ahead and jump into the next set. Go ahead and write down number 3. We'll call this example 2. All right, we have 3 factoring techniques that we've learned. I don't, is that spelled right? I'm having a major brain fart. That looks right? It looks weird. Okay. I think I should stay home today. I'm not doing well. All right. You always start by looking for your GCF first. Take out the biggest thing that you can out of all the terms. After that, if you have a difference of squares, then what we'll do is we'll factor that using the strategy that we learned for that. If you have 2 perfect squares that are being subtracted, you make one plus, you make one minus, and put the square roots there. We probably won't see a lot of that one today. My software just doesn't seem to generate questions that have that very often. But we'll probably see a lot of this. For these ones, we're going to use the box method. Okay, so those are our 3 factoring techniques: GCF, difference of squares, and the box method. Right? You always look for a GCF first. So let's do that first. For this top group up here, what's the biggest thing that goes into 12 and 24? 12. And they both have at least one n, right? So I can take one n out. So if I divide 12 by 12, I get 1. If I divide 24 by 12, I get 2. If I take one n away from this, I'll still have 1 left. And if I take one n away from here, there won't be any n's left. So I divided out a 12n. See if you guys can take out the GCF on the bottom real quick. I'll wait for you. All right. So there's that. Now, in this case, now we're going, if these were exactly the same, we could cancel those out. But they're not, so these are done. We can't do anything with that. But we can work with this here, 12n over 6n. First of all, the n's just completely go away. There's 1n on the top, there's 1n on the bottom, so they just cancel out. 12 over 6, though, what goes? We could divide both those by 6, right? So the top is 2, and then the bottom is 1. So you don't really need to write the 1. And there you go. So I just reduced these. So take out your GCF and then reduce that thing in the front. All right. All right, you guys try number 4 here. See how you do with that. All right, so there's our first step, taking out the GCF. Amethyst, what can we do now? Reduce, yeah. Now in this case, the r's completely cancel, and 10 divided by 10 is 1, so you're just left with this. That's it. Okay. So that was an example of, did you need that still? That was an example where we did factoring, but with GCF. But remember, there's also the box method There's also difference of squares. I don't think we're going to see it today, but it's technically an option. Let's keep going. Oh, I think we'll, let me see, 40. I'm trying to see if there was something to this. No, we'll skip. All right, let's do this one. So go ahead and write down this one. We'll call this example 3. So now, usually you always start by looking for a GCF, but I made these problems have no GCF on purpose, so we're going to skip that. But notice it has 3 terms in it. When they have 3 terms, that's a box method problem. So I'm going to do the top, and then I'm going to let you guys try the bottom, just to review the box method, because that's something that is just hard to get stuck in our brains. But basically, what I'm going to do is I'm going to do the box method, and that's going to cause this trinomial to split up into 2 binomials. And my job is to figure out what those binomials are. So you take the first term and you put it here. You take the last term and you put it in the bottom right. And then we look for 2 numbers that multiply to make n squared. What would that be? N and n. There's only one way to do it, so that's nice. That means it has to be that. Also, 2 is kind of easy. There's only one way to get 2. It's -2. So I know that one of these is 1. The other one is 2. I know that one of them has to be negative. So I'll just pick one for now. Now don't write this until I'm done, because I might have to change it. But here's how we check to see if that's right. Right now I'm guessing that it's n minus 1 and n plus 2 that'll go here. N minus 1 and n plus 2. But we have to make sure it's right. How do you make sure it's right? You multiply n times -1, 2 times n. If these combine to make the middle, then we're good. So 2n take away 1n is 1n, right? It's really close. I need a -1n. So that means I need to try switching stuff around a little bit. Instead of putting the negative by the 1, I'm going to put the negative by the 2 this time. See if that works. It will, because it's really the only other possibility. -2 plus 1 is -1, so now we're good. So I broke this up into n plus 1 and n minus 2. And that's the box method. Why don't you guys try reviewing the box method here for this guy. And we'll see what you guys get. Yeah. So it was asked, is it okay if they're in a different, same as 3 times 2, right? All right, now, you guys see how these things match? So they cancel each other out. And there's that. Final answer. So let's review what we did. It's a long problem. But the first thing we did was I'm going to clean this up a little bit and give you some steps to think about. The first thing we did was we did the box method. How did I know to do the box method on this one? It's got 3 terms. Good job, guys. So 3 terms on the top means that you're going to do box method. 3 terms on the bottom means you're going to do the box method. After you do the box method, you just reduce. Whatever's the same on the top and bottom, reduce it out. Okay? So let's try one more like that, but this time I'm going to let you guys do the whole thing. See how you do with it. I'll give you a little bit of time. Owen, did you factor the top? What did you get for the top when you factored it? Great job. So the top should have been p plus 8 and p minus 4. DeAndre, did you get the bottom? Great, that's correct as well. All right, and then Brianna. What's next? Yeah. All right, guys. I have one more I want to share with you before we call it a day. I'm going to go through it a little bit quick, but I just want you guys to have it in your notes for tomorrow. I'm not giving you guys homework today because I'm not going to be here tomorrow. I'm going to let you guys work on the homework that we would have done tonight in class tomorrow. But I want you to have this example. The last example is just kind of like, it's what we've done already, but it's GCF plus box method. Once again, I'm going to go through it kind of quick, so just write down everything. That way you have it to look at to help you with your homework tomorrow in class, okay? Because I think we're out of here in 7 minutes, so I got to bust through this in about 7 minutes, which is not too bad. There it is. So the last set I did with you guys, we didn't have a GCF. I left that on purpose because I didn't want it to be overly complicated. But now I want you guys to know, technically, you should always look for a GCF. So even though there's 3 terms on the top, we still should take out a GCF. On the top, there is a GCF. It's 3. If I take out the GCF, that's what it would look like. There's also a GCF on the bottom. There's a 9, so I could take out a 9. So the first thing I did was I took out my GCF. All right, the next thing that you would do is you would do the box method on the top here. So as you guys can see, there's 3 terms here, right? 1, 2, 3. So that's a box method problem. I'm not going to show my work for it just because of time, but I will say box, right? So if I did the box method, it would be and I don't know why, like I said, my software doesn't do difference of squares very often, but it's a thing. But I found one, so I included it just in case. It probably won't pop up very often. But this is a difference of squares. This is not a box method. This might be worth writing off to the side just because we haven't seen one like that today. So notice that that's a perfect square, b squared. And that's a perfect square, 1. What's the square root of 1? Square root of 1 is 1. So you're just going to put 1 here and here. Square root it, put your answer there. What's the square root of b squared? It's just b. It's like the square root cancels out the square. So you're going to put that in the front. So you just take the square root of each one. You write it twice. 1 with a plus, 1 with a minus. That's the difference of squares method. We haven't seen it in a little while, but there it is. So from here to here is difference of squares. All right. What can I cancel off the top and bottom? These guys go away, right? But 3 over 9, that can be reduced, right? What can we reduce by? 3. So the final answer then would look like this. 3 divided by 3 is 1. We don't need to write that. So I'll just have b plus 2 on the top now. 9 divided by 3 is 3. We'll leave that there. And then we have b plus 1 on the bottom. But the b minus 1s are just gone completely. All right, so I just did all the factoring, but we did the GCF, box, difference of squares, and reduced. And that'll be it for the day. All right, guys.